So for the second part of the optimization stuff, we're going to look at some examples from economics. We looked at some business stuff, kind of some like cost analysis type of things, and economics I'm sure many of you are taking, and so some of this will probably sound pretty familiar. So if we represent R of X as the revenue function, so this is the revenue that we get from X items. So R of X will most likely just be a constantly increasing function. For every item that you sell, you should hopefully be making more revenue. So if you plugged in like 12, that's the revenue that you'd get from all 12 items total. And then C, for cost, would be the cost of producing X items. Okay, and then dr by dx, that is a derivative. It represents the derivative of revenue with respect to the number of items, because x represents the number of items. So dr by dx, the derivative of the revenue with respect to the number of items. This is something called the marginal revenue. And so the marginal revenue is basically how much money you get, not necessarily per item, but like if you are working on the 12th item, how much would that item cost? If you were working on the 20th item, how much would that item cost? So picture like the cost and revenue of making t-shirts, for example. And I guess marginal cost would be a better example for this. So dc by dx, that is the derivative of cost with respect to the number of items, the marginal cost. So I'm sure some of you guys have probably played a part in ordering t-shirts or ordering sweatshirts or something like that. I know I definitely did that with senior gear. And when you're going through and you're picking out the number of prices, if you get between like 1 and 10 items, you know, something might cost $15 each. But if you get between 20 and 39 items, it might only cost like $12 each. And so normally with things like that, the marginal cost, the amount that it costs to produce each item, goes down as the number of items goes up, which should make sense if you're talking about something like t-shirts or really anything. So the marginal cost, if you evaluated this at, say, like x equals 10, it'd be what it costs to produce that 10th item, which should be different than what it costs to produce the 11th item or the 18th item or whatever. All right, and then maximizing profit is what we're going to be talking about. So maximizing profit occurs when, so max profit occurs when marginal revenue equals marginal cost. All right, so that is when you are going to make the most money, your maximum profit. That will happen when the amount that you get per item is the amount that it costs per item. And so it's basically, this is the same sort of thing as like taking a derivative and setting it equal to 0. You'll see once we look at this example, because that sentence might not make a lot of sense, especially if you're not an econ person. So suppose that the revenue function is 9x and the cost function is this cubic function right here, where x represents thousands of units, so not just a single unit. Is there a production level that maximizes profit? So let's start off with a profit function. So just to be clear, profit is going to be revenue minus costs. Okay, revenue minus cost. So revenue is what you get in, obviously, and then you subtract what it costs you, and then you get your profit. And so when we set this up, we've got 9x, which is the revenue, and then minus the cost, which is x cubed minus 6x squared plus 15x. Okay, and so we are trying to maximize the profit. We've got the profit function right there. Just to get our domain before we start, if x represents thousands of units, the domain of x could be anything from 0 to infinity. You're not going to ever produce a negative number of items, and of course, technically, we could consider that production could go on infinitely. All right, so here's our profit function. What we are trying to do, the derivative of p is the derivative of r, which is dr by dx, minus the derivative of cost, dc by dx. And so the first step in maximizing is finding critical points, and so we would set this equal to 0. So that's what I meant by this sentence up here. If we set this equal to 0, that's basically the same as setting this equal to this, because you would add the dc by dx over to both sides. So maximum profit occurs at the critical point, which is what happens when the marginal revenue is equal to the marginal cost. So that's what we're trying to do. So the marginal revenue is 9. That's the derivative of this piece right here. And we're going to set it equal to the derivative of cost. So that would be 3x squared minus 12x plus 15. Okay, so that's the main idea. So at this point, this is saying each item costs $9. I'm sorry, each item brings in $9, which makes sense. Revenue is usually a pretty consistent thing. So the revenue is just $9 times however many thousands. I don't know if it's dollars or whatever. We set this equal to the marginal cost function. We've got a little bit of math to do. We're going to move the 9 over to the other side. Some factoring will be involved. So we've got 0 equals 3x squared minus 12x, and then plus 6 when I subtract 9 from both sides. Okay, so what I'm trying to do here is I'm trying to factor down. So I'm going to take out a 3. Okay, so that's where I'm at so far. This you should hopefully recognize as being unfactorable. There's nothing that multiplies to 2 that adds to negative 4, so I set up my quadratic formula. So x equals negative b is 4, plus or minus the square root of b squared is 16, minus 4 times 1 times 2 is 8, all over 2a, so 2 times 1 is 2. And so this is 4 plus or minus root 8, which is 2 root 2, over 2, so divide out the 2, and I get 2 plus or minus root 2. Okay, so I can simplify that up. I'm going to get these two values. So, let me show you. So 2 plus the square root of 2. I get one value, and then 2 minus the square root of 2. Okay, so I'm going to write those two values down. Of course, we want our 3-digit accuracy. So 3.414 and then 0.586 to keep that 3-digit accuracy. So they can't both be maxes. So one's going to be a max and one's going to be a min. So what we need to do is set up a sign chart. So it's super, super important that we have a sign chart for P prime. So we've got 0.586 right here, and then the 3.414. So we can set those two up, and then we're going to plug some sample values into the derivative and try to figure out if these values are maxes or mins. So plug something like, I guess 0.5. We don't want to go quite as low as 0 because that's our natural bound here. So if we plug something like 0.5 into this derivative here, this is going to be really small. This is going to be really small. The 6, let's see. Might as well actually do that. So if we plug something like 0.5 into the derivative function, so 3 times 0.5 squared, and then minus 12 times 0.5, and then plus 6. That turns out to be positive. So that is something that we're plugging in between these values right here. Oops, you know what? I should have gone the other way. This is not the derivative. This is actually the opposite of the derivative. The derivative is what I get if I move this stuff over here. So my derivative is actually 9 minus 3x squared plus 12x minus 15. So since this came out positive, it's actually supposed to be the opposite. So this comes out negative. So let's plug something like 1 into this derivative right here. If I plug in 1, I get 9 minus 3, which is 6, plus 12, and then minus 15. And so that will end up positive. And if I plug in something bigger, as big as I want, if I plug in some really big numbers here, this thing is going to overtake everything. Say I plug in like 10. I have 9 minus 300 plus 120 minus 15. This negative value will overtake everything, and the derivative will come out negative. Sorry about that. It's this thing right here that we have to take the derivative of. I was kind of going off this, and that's where this thing came from. Okay, so if we look at this guy right here is a minimum, and so this guy right here is the maximum. Okay, so x equals 3.414. That is the production level that maximizes profit, and so that would be 3,414. Okay, this one right here, that's maximum loss. You get maximum loss at 586 items because you're not producing enough to make up for what the cost is. Okay, minimizing cost. If you are trying to minimize cost, we just talked about maximizing profit. Minimizing cost, this occurs when average cost is equal to the marginal cost. And again, that is something that we will see set up once we look at these equations. So here's our cost right here. Again, X represents thousands of units. Is there a production level that minimizes the average cost? If so, what is it? Okay, so we need to set up something for average cost. Average cost we get by taking the cost function and then dividing it by the number of items. And then that would give you the average cost per item. Okay, so if we're trying to take the derivative of this, we want to minimize average cost, which means we want to minimize this expression right here. That's going to require a quotient rule. So if we take the derivative of this function, here's what we get. So we've got low, d high, minus high, d low, which is 1, and then all over low, low. Okay, so that's our derivative function. What we're trying to do is we're trying to set it equal to 0. And so we're not super worried about the denominator. It would be undefined if x was 0, but of course we've got the same domain that we had up above. Production could go on infinitely, but we can't produce negative numbers of items. So we just want to set this numerator equal to 0. And so we set x c prime minus cx, we set that equal to 0. And so like I said, what's basically happening is, just to show you how this is what we set up here, this is the same as taking x times c prime and setting it equal to c of x, which is the same as taking marginal cost and setting it equal to the average cost. That's what we're doing down here, but I want to get the actual math involved. So c prime, we take the derivative of this function, we get 3x squared minus 12x plus 15. Same thing as up above. Now we're going to plug it in here and set it equal to 0. So if we multiply all of that by x, we get 3x cubed minus 12x squared plus 15x, and then we subtract the cost function. So we subtract x cubed, we end up adding 6x squared, and we subtract 15x. And we want to set that equal to 0. So lots of like terms we can combine up. The x cubed, we get a 2x cubed. The x squareds, we get a negative 6x squared. And then the 15x's will cancel. We are just setting that equal to 0. So we can factor out a 2x squared. Alright, and then we've got x minus 3 equals 0. So the critical points we come up with are 0 and 3. Okay, 0 doesn't count because it's not within our domain. It's 0, but it's non-inclusive. So 3 counts as a critical point. So you always want to actually double check that the 3 is in fact a minimum, and it's this function that we're looking at right here. That is the derivative that we want to plug some values back into. So say we plug 1 in. We have this thing right here, and then over x squared. So if we plug 1 into this beautiful thing, remember it simplifies down to this, we have 2 minus 6 and then over 1. So that comes out negative. Say I plug in something like 10. If I plug in 10, I would have 2,000 minus 600. That comes out positive. So this is in fact a minimum. So x equals 3. This is the production level that minimizes costs. And remember that represents 3,000 units. Okay, next page. We got 2 more problems here. We're going to find a minimum distance, and then we're going to find minimum area. So these are just kind of some run-of-the-mill optimization problems, not really related to any particular topic. So minimizing distance. Which points on the graph of y equals 4x squared are closest to the point 0, 2? Picture. I'm hoping that you read this problem and you're like, oh, I'm going to need a picture. So we set this up. Our graph of 4 minus x squared, we have a y-intercept of 4, and then we have x-intercept of plus and minus 2. So graph that parabola, and we want the distance from 0 to. So that distance, it's going to be like something over here maybe, and something over here. Either way, you should be expecting 2 points. All right, so this is just some sort of xy point, and then this is the point 0, 2. Okay, so we want to minimize the distance formula. So let's write down the distance formula. D equals square root of x2 minus x1 squared plus y2 minus y1 squared. So we are minimizing that. Well, just to throw it out there, just so everyone is aware, when I take the derivative, or if I square both sides, d squared equals x squared minus x1, and then x or y2 minus y1 squared. Minimizing this is the same as minimizing this. If I minimize the distance squared, I might as well be minimizing the distance. So to take this and work with this is going to be a lot easier than working with the square root function. I can avoid a chain rule. Okay, so what I want to do is I want to set up my distance formula. So distance squared is equal to, and what I do with this is I plug in the values that I know. So this is your x2, y2. This is your x1, y1. So x minus 0 quantity squared, and then plus y minus 2 quantity squared. Okay, and we've learned from previous optimization problems you cannot optimize if you're still dealing with two variables. So we make some sort of substitution. Well, here's the substitution. I know that the y value is 4 minus x squared, so I can sub in that right there. So that just ends up being an x squared, and then plus y gets replaced with 4 minus x squared, and then minus 2 squared. So we're just going to keep cleaning this up. Okay, so x squared, and then plus, if I simplify this down, I get 2 minus x squared, and then I can FOIL it out, square it out. So 2 times 2 is 4. 2 times negative x squared is a negative 2x squared, and I have 2 of those. And then x squared times x squared. So simplify this up one more time. I've got x to the 4th minus 3x squared plus 4. Okay, and that is my distance squared. Okay, so I am trying to maximize this function right here. And again, the logic is, if I minimize this, I'm minimizing this. The square root isn't going to make a difference. If this value is at a minimum, its square root is also going to be at a minimum. So I can make my life a little bit easier by just squaring both sides. Okay, so I'm trying to minimize that. So I take the quantity d squared and I take the derivative. So I get 4x cubed minus 6x and then plus 0, technically. And so what I do is I set that equal to 0. So I can factor out a 2x, and that leaves me with a 2x squared minus 3 equals 0. So for my critical points, I come up with 0 by setting this equal to 0, and then I get plus and minus the square root of 3 halves. So here I would add 3, divide by 2, and then square root both sides. Don't forget your plus or minus. So 0 and then plus or minus 3 halves. So what I do here is I set up a sign chart, because I've got lots of possibilities. So this is d squared prime. So I have negative root 3 over 2, 0, and then positive root 3 over 2. Let's extend this a little bit. So I can plug in some different values. Just in case we don't know what this is, we can always go dramatic and plug in something way smaller, like negative 10. So say I plug a negative 10 in here. This would be negative. This would be positive. So this would come out negative. If I plug something in here, like negative 1 perhaps, this would be negative. This would be negative, and so that would come out positive. If I plug in like a positive 1, this would be positive, this would be negative, so the product would be negative. And then something way bigger than root 3 over 2, like 10. This would be positive, this would be positive, so that comes out positive. All right, so that's my sign chart. So I have two minimum values. This is a minimum value, this is a minimum value, which is exactly what we were expecting. I told you to expect two symmetrical points right here. 0 is actually a local max. It's not going to be the max, because obviously as I go down here I get farther and farther away, but it's a local max. It's like I'm the farthest away that I'm going to be for a while. So here I'm kind of far away, then I get closer and closer to 0, 2, and then I just get farther from there on. Same thing as I go to the left. So make sure you're actually answering the question, which points, which means we need the y values as well. And so I plug in to my function right here. So 4 minus root 3 over 2 squared, whether it's positive or negative, this will come out the same. So that's 4 minus 3 halves, which is 5 halves. Okay, so the points. I need positive root 3 over 2, 5 halves, and negative root 3 over 2, 5 halves. So those are my 2 points. Like I said, always make sure you're answering the question. Since they asked for the full point, we need the y value as well. Okay, last one, minimum area. A rectangular page is to contain 24 square inches of print. Margins at the top and bottom are 1.5. So again, this should scream picture. So we've got print like this. Okay, so 1.5 inch margins this way, 1.5 inch margins this way, and then left and right are to be 1 inch. So 1 inch over here, so that's an inch, this is an inch and a half, this is an inch and a half, and then here's all the prints. Okay, so we've got our margins drawn out. What should the dimensions of the page be so the least amount of paper is used? Okay, so what we want is, this is first of all 24 square inches. They mentioned that right here, 24 square inches of print. Let's say this width of the print will be X, the height of the print will be Y. So here's what I know. When I'm talking about the prints, I know that X times Y comes out to be 24 inches. I know that. So now let's talk about the area of the page. So we want to maximize the area. Okay, so the area, this length right here, is x plus an inch plus an inch. So that's x plus 2. The height of the paper is y plus an inch and a half plus an inch and a half. So that is y plus 3. So that is my maximum area. I'm going to try to maximize this, which remember means I need to be in terms of one variable. So I either replace the x or replace the y. It really doesn't matter either way. If I solve for y right here, this becomes y equals 24 divided by x. And so I'm going to replace the y in that second equation so I could maximize. So x plus 2, and then the y gets replaced with 24 over x, and then plus 3. So this one, you could do a product rule. You want to avoid a product rule at all costs, and so we want to FOIL that out before we start to take the derivative. So we've got x times 24 over x. The x's will cancel out, and I have 24. X times 3 is 3x. Here I've got a rational piece. This is going to be 48 over x. And then my last piece, 2 times 3, gives me 6. So one last round of simplifying, I can combine the 24 and the 6. So I've got 30 plus 3x and then plus 48 over x. Okay, so that's our area function. It's all in terms of x. We got rid of our second variable. And so if we're trying to minimize those pages, we want to take the derivative first. So a prime. Derivative of 30 is just 0. Derivative of 3x is 3. And then this, remember, is technically 48x to the negative first, so keep that in mind when we're doing our rules. So this will be a negative 48x to the negative second when we take the derivative. All right, so this becomes 3 minus 48 over x squared. And I can set that equal to 0. And so if I move this term over, I've got 3 equals 48 over x squared. Multiply both sides by the x squared. Divide by 3, and so I end up with x equals positive 4 or negative 4. I don't count the negative 4. That's not in my domain at all. The domain, it definitely just can't be negative. It can be anything bigger than 0, though. So that's my only value of x. We always want to set up a sign chart to make sure it actually is a maximum value. And so we're looking at the 4 here. If I plug in something to the left, like maybe 2, 3 minus 48 over 2 squared comes out positive. If I plug in something bigger like 10, 3 minus 48 over 100, that would end up being positive as well. Hold on one second. So 3 minus 48. Oh no, I'm sorry. This side to the left would end up being negative because you would have like 3 minus, and then this would be 48 over 4 or something like that. And so that would be 3 minus 12. That would come out negative. If I plug in something like 10, I would have 3 minus 48 over 100. That would come out positive. So I keep saying maximum. We are trying to minimize. We're trying to get the least amount of paper. All right, so this does turn out to be a minimum value. Make sure you're actually answering the question. So it says, what should the dimensions of the page be? So since this is x, we want x to be 4, but the width of the page should actually be 6 inches. And then for y, we've got this equation right here. So if x is 4, that would make y 6. But again, y is this measurement, not including the margins. And so we tack on the margins, and that would be 9 inches. So again, make sure you're actually answering the question, and our dimensions are 6 inches by 9 inches.